Are you an S4 student, a VACist, or even then, an all-level teacher? Welcome to this episode, Digital Science for You. I'm Nicholas Norbert. Digital Science and Virtual Lab. You could ask yourself, what is that all about? Well, Digital Science and Virtual Lab is a student learning easily and a teacher teaching with no hassle. Digital Science and Virtual Lab software is a whole all-level science and mathematics curriculum presented in a digitized format. A mixture of 2D, 3D, video animation with text and sound. How it works, all you need is a computer with software and you, the student, and we are ready to roll. Some say physics is one of the hardest subjects. Why? Because the costs of doing the experiments are very high. So you students are left imagining what the experiments are like when drawn on the chalkboard. Take an example, magnetism, when the rays move from the north to the south poles. In fact, on this episode, I've got a physics teacher using a 3D demonstration of electromagnetism, and guess what? He'll be using digital science and virtual lab.
Hello class, I'm Patrick, your teacher of physics today. The topic for today is electromagnetic induction. It is usually taught in senior 4 and students always find it difficult because it is not well handled by teachers. Because imagine if you have 100 students in a class and you need 100 voltmeters, 100 ammeters, 100 magnets, and so many wires for connecting. It can be very expensive to use only the 100 students. Therefore, digital science has come up with a solution to remove this challenge by providing a very conducive and cost-effective way of handling the topic by using or by screening the actions in form of animations which can be viewed on the screen, either of a laptop or any CPU. Right, so today we want to use the digital science and see how to improve our lesson of physics on electromagnetic induction. So we go to our computer, click on senior 4, click on digital science, on physics, and then we go to topic 1, which is electricity and magnetism. Then we click on electromagnetic induction, and we click show. Then we click on learning objectives. We go to number 4.13. Now 4.13 is showing us what we need in order to teach this topic. For example, we need the ammeter, the galvanometer. We need a coil of wire, which we commonly call the solenoid. We need the magnet. And if we are teaching in the traditional way, we always find it a problem drawing that circuit on the board, because you'll have the solenoid. If I did it like this, a student may not know which one of the two wires, for example, this one and this one is on the other side and which one is on this side. At the same time, when you want to talk about a magnet being inserted or plunged into the solenoid, it will be much easier explained using digital science than using the traditional method of talk and chalk. Then for that matter, you end up not making the students to appreciate the subject, and therefore they lose interest and eventually they fail the subject. But digital science has come up with a solution to all that, as we are going to see. Now, in this frame, you can see the white arrows within the coil. This one is here. They are pointing in one direction. As the magnet enters into the coil, those arrows are pointing in one direction. And they are showing that there is an EMF. EMF is short for electromagnetic induction. They are showing that EMF is induced in the coil. And this EMF is induced only as long as the magnet is moving into the coil. Once it is stationary within the coil, the arrows will not be there, as we can see. Now, you can see that as it comes out of the coil, the arrows change direction. If they have been moving from left to right, when you are inserting the magnet into the coil, when it comes out, they move in the opposite direction. Now, electromagnetic induction is simply about, or it deals with production or generation of EMF when magnetic flux interacts with a circuit or a conductor. Okay, as we look at that animation, there are two observations we can make. One, the arrows in the coil are moving in one direction. At the same time, the pointer on the galvanometer is deflecting to the right, and then when it is stationary in the coil, it stays at 0. And when it is coming out of the coil, it goes in the opposite direction, and then back to 0 when it's completely out of the coil. We move to the next frame, 613. Now, in 613, we have a magnet and then a circuit in which we want to observe our induced EMF. We shall click on interactivity and then click on rotate.
I click on rotate.
Okay. When you click on rotate, there is a wave, a sine wave representing the induced EMF in the coil as you move the magnet into the coil and then out of the coil. Now we can click stop, and then we drag the rotation speed from 11 to about 20. When we do that, and then we click rotate again, we shall generate another wave which shows that the amount of EMF generated is much more compared to the previous one when it was at 11. We can click stop. Then we take back the 20 to 11, the rotation speed from 20 to 11, and then we drag the number of coils. The number of coils from 1 to 2, let's say. And then click on rotate. Again, compared to the first time, we had the amplitude of the wave was much smaller compared to this. Now, this is an indication that when you increase on the number of coils, the amount of induced EMF also increases. We can increase both the rotation speed. First, let's stop that one. And then we increase the rotation speed to, let's say, 20, and then the number of coils to 2. And then we click rotate. When we click rotate, you can see that the amplitude of that wave is much, much greater compared to the previous two cases, implying that more EMF has been induced into the coil. Now, this topic here is a very good one, but as I said much earlier, we at times don't give the students what they need. For example, if I went to class and I started talk and chalk, drawing those diagrams alone will take me a very long time. And when at times some of us, when we are drawing, especially the magnetic flux, if this is a magnet, let's say this is the North Pole, and we are drawing the flux, at times we make a mistake and make these lines to cross one another. When we do that, that one is scientifically very wrong.
You're still watching Digital Science for You. Hope you're learning a thing or two about this lesson. You can also access the programs and the sessions via our main offices in Lugogo via the Uma Showground. You can follow us on Facebook and Twitter, CSTSUG. We'll be right back right after this.